Swayam Prabha. Digital India. Educated India.
So in the last lecture we saw the discrete Fourier transform and the inverse discrete Fourier transform. We were about to prove that the transform that we claimed as the inverse discrete Fourier transform was indeed the inverse discrete Fourier transform. We just mentioned that this is the IDFT. We will just have a quick look at the IDFT that we mentioned last time. Then we will complete the proof and have a look at some a few properties of discrete Fourier transforms today. Okay. So, though we have written it last time, we will again repeat it once. This is the Fourier transform, discrete Fourier transform that we talked about last time. Now, in this class and maybe even subsequent classes, we will use x of n and xn interchangeably. It just means the nth sample. Okay. And the inverse DFT we claimed was to get the sample back, n sample back was some constant c or k. We mentioned c last time. Okay. So, now if this is a proper transformation in the going from the time domain, discrete samples in the time domain to the frequency domain, then it is possible to have a inverse transformation restricted to m frequencies in the discrete domain, such that you can get the n samples back, and that is this transformation which we call as the inverse DFT or the inverse discrete Fourier transform. The motivation of course comes from the equation number 3 that is mentioned here, but which is an inverse Fourier transform in the continuous domain. The motivation for the inverse DFT comes as we saw in the DFT also. The motivation comes from the continuous domain transforms, but this is a standalone transform in the discrete domain. X of 0 to n minus 1 pieces of complex information in the discrete domain. Okay. So, let us prove that this indeed is an inverse DFT. Now, to do that I will make use of the slide, since writing it out will be a lot more time consuming. Ignore the change of constant here, where it is c or k. We will see what that value, that constant takes. One thing to notice here is, what we will do is to prove that this is an inverse DFT. We will plug in the value of xm from here, okay, and then show that it indeed is, and I am sorry, then this should have been xk. Okay. Why xk is the change of notation here is, this k is a small k, which is here. Do not get confused, that is why I think I earlier used x c here. So, this can be c. Okay. So, this is x of small k, getting the kth sample back. Now, here if you see in our earlier DFT notation, we have used m as the we have used n here, we are getting the n sample back. Here the here we use k as a sample, so as to avoid the specificity associated with n. Okay. So, now we will go back to the slides here. Now, we are just expanding this out. First, for the first, what we will do is for the inner summation, we will start with k. First, we will start with m is equal to 0, in which case both the expressions will e raised to 0 in both places will be 1. So, k will vary from 0 to n minus 1. So, you get x of 0, x plus x of 1, that is the summation here, x of 1, both the exponentials will evaluate to 1. So, you get x 0 plus x 1 up to x of n minus 1. Now, let us put m is equal to 1. Okay. So, here of course, this n should be small of k. Okay. So, now let us put m equal to 1. So, for m equal to 1, the outer exponential will become e raised to j 2 pi n by n. Okay. So, that is what you will get here. All the terms in the second row, if you notice, will have an exponential. Let's park for the moment what happens to the inner exponential. We will come back to that. We will have this constant everywhere, e raised to j 2 pi n by n. If you see, notice here, they are there with all the terms. Okay. Then what happens when we vary k from 0 to n minus 1. So, for the first term, this exponential will be 0. So, you get only x 0. Okay. Of course, this second exponential is already there, as we saw, because m is equal to 1. Now, for k equal to 1, you get m is already equal to 1, k is also equal to 1. So, you will get minus j 2 pi by n here with the x 1. Similarly, with x of n minus 1, since m is equal to 1, you will get minus j 2 pi n minus 1 by n, okay, and so on. Now, if you go to m is equal to n minus 1. Now, with m is equal to n minus 1, if you plug m is equal to n minus 1 here in this in the outer exponential, you will get this term here. Okay. If you see this term, this will be a constant which will be there with all the terms x 0, x 1, etc., with whatever other exponential will come, but this will be there with all, because m is equal to n minus 1. So, here you can see e j 2 pi n minus 1 n by n, m is n minus 1 here. Okay. So, this the first term will have, because m is n minus 1, you will have n minus e raised to j 2 pi n minus 1 by n, then this will accompany all the terms. Now, let us go to the inner summation, and the inner index will now vary from 0. So, since the first term is 0, the e raised to 0, it will become 1. So, you will get only x 0 plus x 0 into e raised to j 2 pi n minus 1 n by n. The second term will be, that is associated with k is equal to 1, will be k is equal to 1 here, m is already n minus 1. So, you will get x1 plus x1 e raised to minus j 2 pi n minus 1 by n, and this, the constant accompanying term is already there. Now, what is the last term? Last term is k is equal to n minus 1. So, for k equal to n minus 1, what do you get? X of n minus 1. Here both m is n minus 1 as well as k is n minus 1. So, you will get n minus 1 square, which you can see here, and there is one more n minus 1 outside. So, that comes here. Okay. So, it is just a matter of detail that you expand it out and write it down. I suggest you write it down for yourself, so that you get familiar with this. Okay. So, what did we do? Just to repeat, we, for the first row we set m is equal to 0, and then we varied the index k from 0 to n minus 1, then we set m is equal to 1, so on, then m equal to 2, and then the last row will have m is equal to n minus 1. Okay. So, what you do is you fix m at some value and then keep on varying k. Okay. So, now what we will do is, here we have written the terms row wise. So, we have expanded them m wise. Now, what we will do is, we will group the terms k wise or column wise. Okay. We will group all the x 0 terms together, the x 1 terms together, and the x so on up x 2 terms together, and x n minus 1 terms together. Why are we doing that? Because we want to get the sample back. Okay. So, what does intuition tell us? If you are going to get the sample back, that is, this is just intuition, we will prove it of course, is that if you want to get x 0 back, that is for k is equal to n, then or rather we will talk about the converse. If you want to get x 0 back, all other terms where k is not equal to n, all the other terms x 1, x 2, x n minus 1 will whatever is in the bracket should equate to 0, otherwise you will not be able to get x 0 back. Okay. So, this is from intuition, but if you look at the terms here, what are we looking at? If we group the x 0 terms together, what do we get? X 0, that is the first term, x 0 is common outside. Okay. So, we take out x 0, then we get 1 plus e raised to j 2 pi n plus e raised to j 2 pi 2 n, and so on up to e raised to j 2 pi n minus 1 by n. Similarly, for x 1 we will get e raised x 1 plus x 1 into 1 plus e raised to j 2 pi n minus 1 and so on up to e raised to j 2 pi n minus 1 square. Okay. So, this is how it will look like. In general, you will get the first here for x equal to 0, you can see that for the exponential you can write the n as n minus 0. Here you will get n minus 1, for the x 1 you will get n minus 1 terms everywhere. For x n minus 1 you will get n minus 1. This is of course n minus n plus 1 if you expand it out, but it is grouped together. So, you will get n minus 1. So, in general you will get n minus k as in the exponential. So, that is what is written here. Okay. So, you will get here e raised to j 2 pi m by n minus k, where k is now varying from, it is the same, the index is the same as the sample number that you are trying to get back. K is varying from 0 to n minus 1. You can notice it very clearly here. In the first term you have n minus 0, in the second term you have n minus 1, in the second in the second term you have n minus 1, in the third term you will have n minus 2, and in the n minus 1 term or the nth term you will have n minus 1. Okay. So, this is what you will get. So, now for n is equal to What happens when n is equal to, first we will see what happens when n is equal to k. Okay. When n is equal to k, what happens here? This becomes a e raised to j 2 pi n minus k n minus sorry n is equal to k. So, this becomes all ones. Okay. So, 1 plus 1 plus 1 plus 1 plus 1 n times. Okay. It's from 0 to n minus 1. So, n times. So, you will get n x 1 or n x k. Okay. Now, with k is equal to n, you can easily get the sample back. But now with what happens with n not equal to k? Let us see what happens there. K not equal to n. For k equal to n, we saw that all the exponentials will evaluate to 1. So, you have 1 plus 1 plus 1 n times. Okay. So, now what does this become from m is n sorry m equal to 0 to n minus 1? We will just write it down, n minus k into 0. Okay. So, plus e is equal to n minus k. I am just writing it down so that 2n minus k and so on n terms n minus 1 sorry n minus k into n minus 1. Okay. Now, if you substitute say n minus k as k dash, okay. So, you will get the form a is raised to a is of course 2 pi by n, okay, a raised to k dash m. Okay. Now, if this you can easily see is the form of a geometric series and the sum evaluates to upon 1 minus r. Now, what is this? This will become 1 minus e raised to this will go, and since k dash, since n and k are both integers, the numerator which is k dash is also an integer. So, this evaluates to 1. So, you have 0. Okay. So, what in effect you have done is you have got back only the sample that you are interested in, all the other terms will evaluate to 0. Okay. Now, just a quick word about the constants before we move on. We have done with our derivation for we just saw this actually. Okay. So, this is again one n point DFT. We saw that for us to get the sample back, the constant k or the constant c that we used 1 upon c in the inverse DFT should be n. Okay. In general they can be of this form. Okay. If you see many textbooks and in many different contexts, you will see different some places there is for the inverse DFT there is 1 by n, in which case the DFT will have to be 1. Some cases the forward or the DFT will have 2 by n, which we will use in our course henceforth. for relaying applications, because it's I mean, you get the phasor back directly. So if the DFT has a scaling constant 2 by n, then the inverse DFT will have to have the constant as 1 by 2. So the constraint is that if your DFT has a scaling constant C1 and the inverse DFT has a constant C2, then the constraint is that C1 C2 should be equal to 1 by n. We saw that because otherwise we need to get the sample back and how that n comes into play. So that is why C1 into C2 should be 1 by n. So you can have C1 equal to 1, which we use for the derivation, and C2 is equal to 1 by n. We will use this 2 by n and 1 by 2. In fact, we do not require DFT, inverse DFT, we require only the DFT here. Why would we require to calculate the inverse DFT? Suppose we are doing some transmission, we are interested only in a particular set of frequencies, then we do the DFT and we do the transmission, and we get back at the other end, we get back the frequencies of interest. We do some compression and to conserve the bandwidth, and then we get back the inverse DFT, and then from the inverse DFT we get back the samples. In our case, in relaying, we are really not interested in the inverse DFT. So we will not discuss the inverse DFT further in this, but having said that, we just derived it for the sake that to show that it is a complete transformation in itself, because the inverse exists and it is possible to get back. And we will use the constant 2 by n. Maybe from the next class, when we calculate the phasor or from the DFT, we will in our case we are interested only in the fundamental component, but that we will come to when we discuss the calculation of phasor. Okay. The only thing mentioning here, not worth mentioning, and there are, of course, everything is worth mentioning, but everything, the only thing that to keep in mind is, for us we will use the C1, that is for the DFT the constant we will use is 2 by n. Okay. Okay, so that is what is mentioned here. We will now look at a few properties of DFT before we move on to I am sorry, not this one, this is the next. Okay. So, a quick look at the properties of discrete Fourier transforms. Some of them are pretty straightforward, but we will require them in some form or the other. There are many properties, we will discuss only 4 of them actually, which are sort of required for us in the relaying course or the numerical relaying course. In signal processing, you may have seen many, those of you who have studied signal processing may have seen many other properties also. They are of course valid, but for us this is the 3 or 4 properties that we will discuss. The first one is linearity, then periodicity, then DFT symmetry and phase shifting. Okay. Linearity is pretty straightforward. We will prove some or all of them, but some of the proofs are very easy and sort of single step kind of proofs, but we will go through them for the sake of completeness. Okay. So, there are 2 sets of samples. These are 2 sets of discrete samples, finite sets from x0 to xn minus 1 and y0 to yn minus 1, and the corresponding DFTs are x of m big and y of m. Then if you were to add the 2 samples, these are of course real numbers. So, if you were to add the 2 samples and get the sample set x0 plus y0, x1 plus y1, so on up to xn minus 1 plus yn minus 1, the DFT of that set is given by x of m plus y of m. Actually pretty straightforward. We will just there is nothing but to it, but we will just have a look. Okay. So, if you add the samples in the time domain, the frequency domain output also gets added. Okay. So, what do you have? You have we had x n plus y n is equal to x 0 plus y 0, x 1 plus y 1, x 2 plus y 2, so on up to x n minus 1 plus y n minus 1. This is the sample set. Now, what is the DFT of say for x n alone will be given by now remember that we said that is the same as x of n, just for convenience that we are using this, and y of this is y of m is given by okay. So, now the DFT, if these were the samples, then the DFT of these samples will be given by DFT of these samples will be given by which is nothing but okay. So, this is what we wanted to prove. Okay. The second property is periodicity. We will just have a look at that and then come back and prove it. Okay. So, what do we have? We have a after m greater than n. Okay. We have evaluated up to n minus 1. After n means greater than n minus 1, or that is m greater than or equal to m sorry, m greater than or equal to n, it shows periodicity. Okay. So, what does it mean? That x of m is the same as x of n plus m, is the same as x of 2n plus m, 3n plus m, minus n plus m, minus 2n plus m, or ln plus m, where L is an integer, L or k, whatever the constant that is chosen. Okay. So, very simple, just plug it in. Again we will do it because it will just help us get the concepts of the DFT and the transform more get the concept right in our minds. Okay. So, what we are saying is we are claiming, of course, we will prove it, k is some integer k okay. Now, we will see what proof of this is. What is x of k n plus m? We will just plug that in into our okay. So, what is this? with n and k both being integers. Here what does this term evaluate to with n and k both being integers? Okay. So, this evaluates to which is nothing but x of m. Okay. So, so far the proofs were quite simple and straightforward. The next one is there is also a simple proof which we will see, but we will also go through the rigor of a more detailed proof just to again get the concepts right. Is the what we did not mention till now, of course we are discussing the property of DFT symmetry. What we did not mention till now is that we have taken the samples xn to be real. Okay. If they are complex, then this DFT symmetry property will not hold. Okay. Now you have if we have taken n samples from x is equal to 0, I am sorry, from n is equal to 0 or x0 to xn minus 1. Okay. So, they can contain at the most n bits. I will not use the word bits because it has a specific meaning here, but it can at the most have n bins or n pieces of information. Okay. So, now when you go to the frequency domain, you have the xm's are where m also goes from 0 to n minus 1. So, you have n there also you have n pieces, but they are complex numbers. Okay. So, you have actually 2n bits or 2n pieces or 2n bins of information. So, you started with n pieces of information and you are getting 2n. So, this does not seem right. Okay. So, there has to be some kind of repetition somewhere. Okay. So, this is what the DFT symmetry property shows. Okay. What it says is the x of n minus m, okay, where n is the number of samples, is the complex conjugate of x of m. Okay. So, or the other way, I mean x of m is the complex conjugate of x of n minus m. What it means is that the magnitudes of x of n minus m and the x of m are same, but there is anti-symmetry in the angles. Okay. The angle will be minus. We will just prove that. Okay. So, what we are proving now is DFT symmetry. Okay. So, just to repeat what we have said, so that we have got n samples x0, x1, okay, and from when we do a DFT we get x of 0, x of 1, x of n minus 1, okay, and these are n samples. Here you have 2n, okay, because these are complex numbers. Okay. So, so what we are saying is x of n minus m is a complex conjugate x of m, which means that you have symmetry in angle in magnitude and anti-symmetry in the angles, or rather the other way around. So, what this means is, so suppose you have this is x of 0 here, then x of n minus 1 will be the same. Okay, so if you have this is x of 1, then n minus 2 will be the same. X of 1, 2, and then n minus 3 will be the same. Okay. Similarly for angles. Angle of x of 0 is actually a DC quantity, so it does not make sense. So, that will be 0 only. So, say angle of x of 1 in this is this. So, n minus 2 will be this. If angle of x of 2 is this, then n minus 2 will be this, and so on. Okay. So, you have symmetry in magnitudes and anti-symmetry in angles. Okay. We will prove it. The proof is slightly long. We will also discuss a quick and compact proof after that, because there are many ways of proving this. But we will discuss it because we will also get an not an alternative form, but similar form of DFT, which is important, which we can use in other formats also. So, we have periodicity. We saw the periodicity property. We have x of 0 is equal to x of n, then x of 1 is equal to x of n plus 1. So, similar just to generalize, x of n plus k minus 1 is equal to x of k minus 1. Okay. So, we will write our DFT expression. Here we are not using the constants, etc. We will use that when we calculate the phasors, just to keep our life simple. Okay. So, now here what we will do is, we will split this summation as up to say k minus 1, and then I am sorry, we will I will write it here, so that we will split this summation as 0 to k minus 1, and then k from k to n minus 1. We had a series from 0 n from 0 to n minus 1, just split it in the middle, or I mean whatever k, as 0 to k minus 1 and k to n minus 1. So, this will become okay. So, now this will become n is equal to 0 to k minus 1 x of n, the same n is equal to k to n minus 1 x of n minus j 2 pi m n by n. Okay. Now, what we will do is just we will since there is a sorry, here it should have been a summation first. What have we done here? This is what have we done here? We have just added here where m is an integer. So, this is actually 1. So, we have just added a term like this here, so that this becomes okay. So, this index now we will change. Okay. So, what are we saying now here? Did you notice this? Now, we are going from, we have now got a sequence from k to n to n minus 1, and then from n to n minus n plus k minus 1. So, we have got a whole sequence. So, we can get this as n plus k minus 1 x of n e raised to . Okay. So, this is a this is an alternate form of the DFT. Okay. Instead of varying the index from, we are, of course, we are taking n samples only from, instead of going from 0 to n minus 1, we are going from k to n plus k minus of 1. Okay. Now, we have to compute the shifted DFT. Okay. So, what does that say? X shifted, we will just call it x shifted for the sake of convenience, shifted by k samples is e raised to j. I will just state it and then we will go for the proof, and into your okay. Now, we have here we have what samples did we have? we have shifted the samples from 0 to instead of starting at x 0 we are starting at x k, okay, x k plus 1 up to. So, instead of this what we will do is we will write the samples as y 0, y 1, y n minus 1. Okay, so, we are just proving this expression. So, we have this is the shifted sequence. So, the DFT of the shifted sequence which we have called x x shifted of m just for the sake of convenience, according to our definition gives n is equal to, or according to our earlier definition, not the alternate form, because we are just taking the samples as y n. Okay. K plus m. Okay. So, now what we will do here is I will just write it a bit. Okay. We will add a term here, okay, e raised to j 2 pi okay, just some small manipulation. Okay, you just this k here which we have added has been, we have just plus k and minus k is what we have done. Okay. We will 2 pi m n by n, and we will vary the index from n is equal to k to n plus k minus 1. Okay. So, this n this k we have now adjusted in the index, okay, which is nothing but the alternate form of the DFT that we have already derived, which is all nothing but x of m. Okay. So, shift in the samples in the time domain, you have shifted the samples by k. Instead of starting at 0, you are starting at k, where of course the signal has to be periodic. The samples also have to be repetitive or repeat themselves after a certain period of time. Then if you shift it by k, then that will manifest itself as a phase shift in the DFT or a phase shift in the frequency domain. Okay. So, there is a proof in the books in the book by Lathi, BP Lathi. There is a the explanation is quite simple and elegant. So, let us say that is also known as a circular shift property of DFT. So, let us say that there are we have samples. This is very simple and elegant proof, x 1 so on and so forth up to x of n minus 1. Now, if the samples instead of x 0 we are shifted by say n naught, we are just taking some or say let us stick to k. The samples are shifted by k, then again we will just write down this is the this is the DFT, and the inverse DFT is given by okay. So, the original sequence here is given is x 0 to x n, and the shifted sequence is given by is shifted, the sequence is shifted by k. Now, suppose there is some you call it the shifted sequence as say x of tilde, and the DFT of that is given by, let us claim that the DFT of that is given by x of n e raised to j. Okay. Now, let us plug it back into this and see what we get back. Okay. We are just claiming that there is some shifted sequence, the DFT of which is given by this. Now, we will see what we get back. So, we will shift up, instead of this x m here, we will substitute this value in that x m and see what we get back. Okay. So, in the original definition, if you see here, from this, if this was n, we were getting back x of n. So, if this is k plus n, this is k plus n, we are getting back k plus n, x of k plus n, that is the proof. Okay. So, if we have a shifted sequence x of k plus n, the DFT is given by this. Okay, rather the DFT is given by okay. So, we will stop here for today, and from the next time we will see we will rather start with the estimation of phasor, but before that we will see the equivalence between fast Fourier transforms and the sequence components. So, we will stop today's lecture here.